Hey guys, in this video we're going to introduce electron configurations. So let's first talk about what an electron configuration is. To me, an electron configuration is like a GPS code. We give like a city, like if we were to give our address, right? I live at, I'm not going to tell you where you live. You thought you got me. But let's say I live at 110 Sally Street, okay? 110 Sally Street, and I actually live in Pinson. So 110 Sally Street, Pinson, that's like my GPS coordinates on to where I live, right? You can do those for these electrons as well. Remember, the Heisenberg uncertainty principle means we don't really know the exact location of these electrons, but we can figure out just a roundabout way of where they probably reside. So an electron configuration is kind of like a GPS code to pinpoint where those electrons are. And you know that different things have different number of electrons. So there might be an address for one electron, but the other electron will have a very different address according to where it resides. So where this goes into is different orbitals, okay? So you have s orbitals, p orbitals, and d orbitals. S orbitals is just one configuration, and it's mainly spherical in shape. Okay, this space that you see right here, that is where the electron is probably residing. Okay, we call this the s orbital. These are very low energy orbitals. So low energy orbitals there. Then you have p orbitals. So these spots, we call this like a dumbbell shape. All right, this is like a dumbbell shape. These planes, so you can have the x plane, the y plane, or the z plane. That is where some of these electrons can reside. So we have actually 3 different planes in which these electrons can reside. P orbitals are a little bit higher in energy than s orbitals. And then you have d orbitals. There's actually supposed to be one more picture here, but d orbitals can be in 5 different positions. So that's why we have 1, 2, 3, 4, 5 different things. Now, if you've ever done electron configurations before, you remember how you have to put like your little arrows in here in your different orbitals. So s orbitals get 1 line, p orbitals get 3 lines, and d orbitals get 5 lines. This is something called orbital notation. And the reason why each of them gets this is because of the different planes that they could, those electrons could actually reside in. S orbitals can hold 2 electrons. P orbitals can hold 1, 2, 3, 4, 5, 6 electrons, and d orbitals can actually hold 10 electrons. Each little space that you see here only holds 2 electrons. So this is what we see when we do orbital notation. If you have no idea what I'm talking about right now, it will make sense when we cover it in just a minute. Okay? So let's go on to the next page. So if you are familiar with electron configurations, now the s, the p, and the d orbitals might make sense. You have these 2 here, which are your s orbitals. You have your d block, which is your transition metals, and you have your p block, okay? So again, an electron configuration is kind of like coordinates. It's kind of like an address. So if I wanted to do the electron configuration for, let's say, lithium, okay? Lithium resides right here. So I would start at the beginning and kind of like a typewriter. You just keep on going until you hit that spot. So there's 1 S1, 1 S2, 2 S1. So we go 1 S2, 2 S1 would be the electron configuration for lithium. Now let me explain what all of this means. 1, this number in front, or the 2, whatever you have here, These numbers represent the period or the energy level. Periods or energy levels are your different rows. So you see that this first row is the first energy level. The second row, second energy, third, you guys get the idea. This, the S, that represents the orbital, what we just talked about. So what type of orbital that those electrons reside in. Is it spherical in shape? Is it dumbbell in shape? Whatnot. And then the 2 means how many electrons that reside in that orbital. So this is saying that you have lithium, which has 2 electrons in the 1s orbital and 1 electron in the 2s orbital. Now let's do carbon, which is right here, I believe. All right, so its electron configuration would be 1s2. You see I've taken care of those two. 2s2, taking care of those two. 2s2. And then 2p2. You see I'm just like following a roadmap until I get to that particular element there. Let's do one more. Let's do iron. Iron resides in this area right there. So that's where iron is. So if I want to do the electron configuration, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and what do you notice here? Once you hit this D block, you're actually moving up an energy level. The reason for this is because really where these guys should reside is on this level here. But the periodic table is arranged to where the properties kind of meet. And so these transition metals fit along with the properties here, but where their electrons reside are actually in an energy level lower than that. So once you hit this D block, you bump down an energy level. Okay, so let's start again from 3p6, 4s2, then you bump down an energy level, 3d6 would be the electron configuration for iron. I can also do orbital notation for this. So orbital notation for lithium that we started with, I would have 1s, and 1s gets 1 block. There's 2 electrons, so I draw an up arrow and a down arrow. The arrows, whether they're up or down, just denotes the spin on an electron. It kind of relates to quantum numbers, which we don't teach in this class anymore. So therefore, all you need to know is the arrows represent a different way that the electrons spin. Then you have 2s1, so 2s, and you just have 1 arrow that's in there. The electron configuration for carbon would be 1s2, so 1s, which gets 2 electrons, 2s2, so 2s, which gets 2 electrons. Always do up arrows first, then down arrows. And then 2p2. P blocks actually get 3 bars, so that's 2p. Now, you don't stick both of these electrons in the same thing. They want to be spaced out. The reason why, when I put electrons in the same area, you have something called Electron-Electron Repulsion, which means there's an electron that's negatively charged, another electron which is negatively charged. Guess what happens when you put 2 negative things together? They repel. So what you're doing here is you're minimizing electron-electron repulsion. They're going to try to stay as far away from each other as possible. So this would be my orbital notation of carbon. If I wanted to do orbital notation for iron, that would take a lot of paper, but I would draw 1 with 2 arrows, 1s2, 2s2, 2p6. I would fill out this whole entire thing. There's your 2p6. We would have 3s2, so 3s, 1, 2. We'd have 3p6, so 1, 2, 3. That would be 3p, 1, 2, 3, 4, 5, 6. Notice how I'm putting up arrows, spacing them out, then filling them in. And then it would be 4s2, 4s, 1, 2. And then it would be 3d6, where D block gets 5 bars. So 3d. And it's 3d6, so it'll be 1, 2, 3, 4, 5, 6. And this would be the orbital notation for iron. There's also one other thing that you can do. So this is called the complete electron configuration. This is called the orbital notation. And you also have what you call a shorthand or noble gas configuration. A noble gas configuration is where you put the noble gas before you reach your thing. So let's do iron again, which is here. So the noble gas that comes before iron is right there. Crap, I don't have my periodic table to know what it is. I do know what it is. It's argon. All right, so argon, I put it in brackets. So what this right here is telling me is, hey, it's the electron configuration for argon, so I don't have to do the rest, anything that comes before it. Then I start from argon. So now I have to go to 4s1, 4s2, and then 3d6. So this is called the noble gas configuration. It's a shorthand version. Now AP, if it doesn't say write the complete electron configuration, then you can definitely do this. But most of the time, it will say write the complete electron configuration, so I got to start from the very beginning. So I wrote the electron configuration for iron here again. Now, not only do we have to do electron configurations for just neutral atoms, all right? So iron here, you see that's not an ion. It's just the neutral iron at its ground state. Nothing's happening. No electrons are jumping energy levels or doing any of that stuff. So all of these electrons here are what we call in the ground state. And we talked about in the last video, ground state just means at its lowest level, and they're not jumping energy levels, okay? So not only do you have to know how to do electron configurations for something like this, but you might also have to be able to do an electron configuration for the ions. So let's see how this is, different. This Fe2+, what does that mean? This 2+ means that it has lost 2 electrons, all right? So I've lost 2 electrons. Now, that means that if I look at this electron configuration, it's basically this electron configuration minus 2 electrons, right? But here's the trick. You need to know which electrons it loses. Whenever you have atoms that lose electrons, the type of electrons it's losing is called the valence electrons. So you might be familiar with this, you might not. Valence electrons means the outermost electrons, the outermost. And so here's technically what's happening with this iron. You have 1s2. So remember how we drew those like energy levels? So you have 2 electrons in the first energy level. 2s2, 2p6. That means you have 8 electrons in that second energy level. 3s2, 3p6. That means you have 8 electrons in this energy level. 4s2, you have another energy level. And then the 3d6 means that there's actually 6 more in this third energy level. Okay? There's your nucleus right there in the center. Valence electrons means the outermost electrons. So you're trying to first take away these electrons that are in the outermost shell. You always take away your valence electrons first whenever you're losing electrons. And we'll be talking more about this when we talk about something called ionization energy when we get to the periodic trends portion. So where do these outermost electrons reside? Well, if this is the first energy level, that's there. Second energy level, that's there. Third energy level, that's there. Fourth energy level, that's there. The fourth energy level for iron is the outermost energy level. So where am I going to be taking electrons away from? I'm going to be taking both of those electrons away from the 4s orbital. Okay? So what would my electron configuration for iron be? It would be 1s2, 2s2, 2p6, 3s2, 3p6. I've taken away those, so now it's just 3d6. This would be the complete electron configuration for iron 2+. What about for iron 3+, Fe3+? How many electrons have I taken away? That means that I've taken away 3 electrons. Well, where do I take away those electrons from? I only have 2 in the s orbital. So I'm going to take away those 2, but I have to take away 1 more, right? That's when I'm then am going to take away another one from the outermost, and that outermost is 3D. So my new electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. That would be the electron configuration of Fe3+. Now, here's another question. What about if I have something that's a minus charge? What does a minus charge mean? A minus charge means that I've added an electron. So let's look at F minus. Well, fluorine would have an electron configuration of 1s2, 2s2, 2p5. So this is fluorine, neutral fluorine, and all in its ground state. F minus means I've added an electron to that. So what I'm going to do is just say 1s2, 2s2, 2p6. So this is the electron configuration for F minus. One more thing I want to throw at you. If I have something that has an electron configuration that is the same electron configuration as something else, we give that a special term named Isoelectronic. I want to introduce this because you'll see it on your exams. AP uses this term. Iso means same. Electronic means same number of electrons. Mind-blowing, okay? Isoelectronic. So let me give you an example of isoelectronic. F minus has this electron configuration, right? Well, guess what the electron configuration of neon is? Neon's electron configuration is the same as this. There's something else that's isoelectronic to that. Na+. If you were to do the electron configuration for Na+, remember that plus means it's lost an electron. It will also have this electron configuration. Does that mean that they're the same thing? No. But they have the same number of electrons, and we give that term isoelectronic. So that's how we do electron configurations. You guys are going to be doing lots of practice in class. And if you are having trouble with this, or maybe you're not as familiar, you don't remember it from pre-AP or whatnot, then I can give you guys some extra videos, or I can meet with you one-on-one to help you with that. Before I leave you, I want to introduce these other terms: magnetism, Pauli exclusion principle, and Hund's rule. So those are the last 3 things that we're going to do. So let me clear my board and then we'll get to it. So magnetism. You have some elements that can attract a magnetic field, okay? And those things that can attract a magnetic field, we call them paramagnetic. And so we don't necessarily need to know which ones do or which ones don't, but we need to understand why. And we could probably figure out which things could potentially attract a magnetic field or not. So paramagnetic means that it does attract a magnetic field. I'm just going to put magnetic field in my so awesome handwriting here. Okay, so paramagnetic, it attracts a magnetic field. How does it do that? Well, it all depends on if you have paired or unpaired electrons. If you have, let me say it this way. If you have any unpaired electrons, then that means that it will attract a magnetic field. Okay, and how I know if I have unpaired electrons or not, remember how we were talking about orbital notation? So let's say I had an orbital notation in the D block, 1, 2, 3, 4, 5. That was like this. So this would be let's just do iron. Right? Didn't we say that the valence electrons, besides the 4s, was 3d6, right? So this is the 3d that we see here. It's 3d6. Hopefully you all know this, but iron attracts a magnetic field. Basically, a magnet will attract to iron as a metal, okay? Well, how is that the case? Well, it's because I have unpaired electrons here. You see how this. I have a lot of unpaired electrons here. So anytime I have unpaired electrons, I can attract a magnetic field. The opposite of that is known as diamagnetic. I think diamagnet, it does not attract a magnetic field if that's the case. So diamagnetic means it does not attract a magnetic field. And if I have something that is diamagnetic, what I would actually see is every single electron would be paired completely. An example of that is zinc. Okay, zinc does not attract a magnetic field. I can take a piece of metal of zinc and try to put it to a magnet and it won't stick together. But if I take iron and try to attract it to a magnetic field, it will. It's all based upon the pair versus unpaired electrons. The next thing is the Pauli exclusion principle. So I'm just going to slowly say this, you can write it out. The Pauli exclusion principle says no two electrons in an atom can have the same set of 4 quantum numbers. Now, personally, I don't know why this is still in AP because they took out quantum numbers. You guys don't know what quantum numbers are. I'm not going to teach it because it's unnecessary in my opinion. But the Pauli exclusion principle says that no two electrons in an atom can have the same set of 4 quantum numbers. For the Pauli exclusion principle, you just need to know the definition, and that's it. And the last one is Hund's rule. Hund's rule says that the most stable arrangement of electrons is that with maximum number of unpaired electrons. Now, I do want to go a little bit more in depth with this, all right? So the most stable arrangement of electrons is that with a maximum number of unpaired electrons. So for Hund's rule, we want unpaired electrons. That is the most stable arrangement. So that means that the most stable arrangement for something in the D block would be this, a D5. You have no paired electrons here, right? It would attract a magnetic field, right? But I have no electrons that are in the same thing. here's the reason why. This goes back to the whole electron-electron repulsion, okay? If I have two electrons residing in the same space, they're going to try to repel each other. If they try to repel each other, that's going to throw things out of whack. I'm not going to be stable, okay? So if I want my atom to be stable, then I want those electrons to be as unpaired as possible to minimize the electron-electron repulsion. So for magnetism, you might have to apply it a little bit and like explain why it's magnetic or not versus it with its unpaired electrons. For Pauli exclusion principle and Hund's rule, really honestly, you just need to know the definition and that's it. So that's electron configurations. I can post another video that maybe can explain a little bit better than I can, but mainly just doing lots of practice will help you with this. So I hope that's a little bit helpful, and I'm sorry if this video sucks and I confused you. So for some reason, I do really bad explaining this introductory type stuff. So if you definitely have any questions, just let me know.